Hello. Welcome to the Mechanics Training Workshop. We're going to learn to build a wheel by hand, starting with the choice of components and the type of spoking, how to true a wheel, and then tires and tubulars, including tips for the professional. All of these stages are illustrated by sequences that will guide you step by step. I wanted this to be as complete as possible, and so have called the specialist Gerd Schraner. Hello, I'm Gerd Schraner, and I'm a wheel builder. Wheel building is my passion, my life. We've tried our best to make everything easy to understand for beginners and amateurs, as well as for professionals. Our main objective is to pass on the fascinating art of wheel building. Building a high-tech wheel is time-consuming and expensive. Therefore, it only makes sense to use hubs from well-known, experienced manufacturers. Cheap products and homemade hubs do not belong here. Here are the different types of hubs: a rear road hub, a rear mountain bike hub with disc brake mount, free ride hub for disc brake mount, tandem hub, a large flange track hub, a small flange track hub, a BMX front hub, a BMX rear hub. And here is an old rear hub with a high flange and a small flange. Here we have a cutaway view of a high-end rear hub. With 1, 2, 3, 4 industrial bearings, then a star ratchet system, and 2 labyrinth seals. Let's look at the overlock nut dimension of some popular hubs. Before we had a front road hub, and this one here is a front track hub. Both have a built-in width of 100 millimeters. A rear road hub, 130 millimeters. A rear track hub, 120 millimeters. And a rear mountain bike hub, 135 millimeters. The raw material for high-end spokes is 1810 stainless steel wire, which is composed of 18% chrome, 10% nickel, and 72% iron with additives. There are 4 types of spokes used for building wheels. This is a straight gauge spoke. It has the same diameter from the spoke elbow to the thread. The disadvantage is that due to the stiff middle section, the loads for the elbow and thread are too high. It's not well suited for use in high-end wheels because it's not elastic. This is a double-butted spoke, which means that this spoke has a smaller diameter in the middle than in the elbow and the thread. This is called a triple-butted spoke because it has 3 different spoke diameters, the largest on the spoke elbow, the thinnest in the middle, and the third diameter on the thread. These are bladed spokes. They're more aerodynamic and look more aesthetic when the wheel is moving. There are 2 different types. The first is not as wide, but it fits in an ordinary hub without having to slot the hub. The second is wider, and it requires a special hub which has been slotted at the factory to match this type of spoke. The resistance to breaking of a butted spoke is very high. When under excessive load, it reacts in a similar way to the straining screw used in the machine industry. However, if the load is too high, the middle of the spoke is stretched until it breaks at this spot. Spoke failures on the spoke elbow, on the other hand, are caused by fatigue. The causes are the play between the hub flange and spoke and/or insufficient spoke tension. The length of a spoke is equivalent to the distance from inside the spoke elbow to the end of the thread, or the end of the spoke. It's measured with a ruler or a special spoke ruler. As we can see, the spoke length here is 266 millimeters. The spoke length is chosen correctly when, on the properly tensioned wheel, the end of the spoke is lined up with the top of the nipple head. This way, the entire threaded part of the nipple head holds the spoke. If the spoke's too short, then the nipple head can break off due to overload. This is a so-called rated breaking point. In high-end wheel building, we work with two different nipple heads. The round head nipple is most common. And this is the hexagonal head nipple, which is used for extremely high spoke tension, especially with wheels with a reduced number of spokes, or with V-profile rims. Nipples exist in lengths of 12 millimeters, the most common, followed by 14 millimeters and 16 millimeters. Most nipples are made of brass. They are mechanically more solid and more resistant to corrosion than aluminium. However, they are heavier. Aluminium nipples, raw or color anodized, are 3 times lighter than brass nipples. Aluminium nipples reduce the dynamic weight of a wheel considerably. Here are 32 brass nipples with a weight of 30 grams, the quantity necessary for 1 wheel. For the same weight, we have 102 aluminium nipples, enough to build 3 wheels.
The
rim is the component of the wheel that is subjected to the most stress. Radially and laterally, it must withstand high loads. The principle of the rim is one of a circular, tensioned spring, which must absorb peak loads while riding. For high-end wheels, we only use hollow section rims. These may or may not have eyelets. Rims welded on the rim joint are superior in terms of circular movement and stability to those that are mechanically jointed.
Wir haben zwei Ursachen
There are two causes for spoke failure.
führen. Die
The
erste
most common is insufficient spoke tension.
ist die zu schwache Speichenvorspannung. Wir haben hier,
Here we have a wheel under load, and
und wie
as
man
we can
sieht,
see,
sind
now
jetzt
the
oberen
upper
Speichen
spokes are under load
entlastet
and the lower
und
spokes
die
are
unteren
not
Speichen
under
sind
load.
entlastet. Ich drehe jetzt das Laufrad.
I'm
Es
turning the
sind
wheel,
vorher entlastete
and now the spokes that were not under load before are under load.
Und die
And
vorher
those that were
gespannten
under
Speichen,
load before are no longer under load.
wir nennen das
We call
Lastwechsel.
these cycles load changes.
Wenn der Fahrer 2000
When a
Kilometer
cyclist rides 2,000 kilometers with the same wheel,
sind
there will
das
be 1
1
million load changes.
Bei einem Laufrad
On a wheel with 32 spokes,
sind es
there are
32
32 million load changes.
Lastwechsel. Da passiert
So there's a
also
lot going on.
die Speichen
The spokes move in the hub flange as soon as they are unloaded.
sobald sie entlastet werden. Es ist dann nur eine
So
Frage
it's only a
der
question
Zeit,
of time until the spokes break from fatigue.
durch Übermüdung brechen. Wir haben auch eine
We also
torsionale
have
Belastung
a torsional load.
und bei
Lateral movements of the
Bewegungen
bicycle
mit dem
cause
Fahrrad
this to happen.
passiert dann noch Folgendes. Abhilfe schaffen wir
To
mit einer
prevent this, we
optimalen
use optimal spoke tension, which means as high as the rim or its profile allows.
Respektive deren Profil erlaubt. Hohe Felgen mehr, flache
High
weniger.
profile rims, more tension,
Gute
flat rims, less.
Speichenvorspannung werden nämlich die
With
zwei
proper spoke tension, the two spokes under the maximum load in the upper half of the wheel are supported by all the neighboring spokes in the upper half of the wheel.
oberen Laufradhälfte unterstützt.
The second cause of spoke failure is the play between the spoke and the hub flange. The connection between the hub and the spokes are put under stress by the load changes. If the spoke sits without play, nothing happens. If there's a bit of play, the spoke elbow moves with a jolt at each turn of the wheel. It becomes stressed and the material becomes brittle. The spoke breaks. To prevent this problem, we test the connection by hand. If we feel the slightest bit of play, then washers should be used under the spoke heads. Washers should always be used with 1.8mm diameter spokes. If spoke breakage is a problem with wheels that have been ridden, we change all the spokes, but this time we use washers under the spoke heads. This spoke broke at the spoke head, a classic break due to fatigue. This spoke broke due to a one-time overload. This took 2,300 newtons. We can optimize the quality of the wheel we're building by using only double-butted spokes. and by tying and soldering the spoke crossings to better stabilize the spoke structure. The classic number of spokes was 36 for many years. Today, however, with the improvement of wheel components for both mountain bikes and road bikes, 32 is most common. The more spokes used, the more stable the wheel. The higher limit is at 36 spokes. Wheels for track sprinters often use 40 spokes. Tandems, 40 or even 48 spokes. Fewer spokes mean less weight, but wheels must then be built with a higher tension. This in turn necessitates a more stable and therefore heavier high-profile rim, which makes the task of reducing the dynamic weight of the wheel more difficult. For this reason, it's better to use more spokes, which makes the wheel more laterally stable, with high rims and alloy nipples. To illustrate, let's take a wheel with a high-profile rim and 24 spokes and put it on the scales. We read its weight. And now, a 28-spoke wheel with light rims and alloy nipples. It's much lighter. There are many steps to building a wheel. Determining the correct spoke length. Preparing of the rim, the hub, and the spokes. And spoking. Truing the wheel laterally and radially. Dishing the rim. Optimizing the spoke tension. Repeatedly cracking or de-stressing and retruing until the wheel stands. And finally, the final check. Working time, 1 full hour. Then there's additional tying and soldering work for another half hour. Radial spoking can only be done on a front wheel with rim braking. But it's important to note that most hub manufacturers do not recommend this type of spoking and decline any responsibility or warranty in the case of fissures or breakage. A few top hub manufacturers make hubs specifically for radial spoking. There are no big advantages to radial spoking. However, the look of rotating spokes can be fascinating. Tangential spoking is used whenever the driving and braking forces need to be transmitted from the hub to the rim. The more tangential the spokes run to the hub flange, the more direct the driving and braking forces are transmitted. It's for this reason that radial spoking is not used on a front disc brake wheel or on any rear wheel, whether it's disc or rim braked. With tangential spoking, we can cross the spokes once, twice, 3 or 4 times. Here, in this example, we have a one-cross wheel. This spoke crosses another spoke once. On this wheel, we have double-crossed. One time, two times. Here we have three-crossed. Once, twice, and three times. This wheel has been four-crossed. Once, twice, three, and four times. Quad crossing only makes sense on large flange hubs. If the flange is too small, the following happens. Every spoke lies on the head of the adjacent spoke. We've said that quad crossing only works on large flange hubs. This here is a small flange hub, and this hub is a large flange hub. One can easily recognize the difference. We speak of a large flange hub when the diameter is at least 66 millimeters. Patterning the spokes symmetrically or asymmetrically does not make a difference in the quality or durability of the wheel. The pulling and braking spokes are under the most stress. So we place them with the spoke head inside the hub flange. This way, these constantly stressed spokes will have a smoother angle in relation to the rim. Lastly, concerning the question of symmetric or asymmetric spoking, where pulling and braking spoke heads are either in or out, we'd like to mention that we've tested these variants over the years and have not perceived any difference in quality. This doesn't mean that we spoke one way one day and another the next, depending on our mood. No, we always keep the same method, for example, with disc brake wheels using this pattern. We have two popular systems for calculating spoke lengths. The easily understandable DT Swiss table. We only have to deal with three measurement steps. Rim diameter, 538 millimeters. Center of hub to center of flange, 34 millimeters. Pitch circle diameter, 36 millimeters. On table A, we have the rim diameter, and here the distance from the center of the hub to the center of the flange. And at the intersection of 538 and 34, we find the number 271. Table B, 32 spokes, 3 crossed. with pitch circle diameter of 36. Intersect at the number 8, which we then deduct from the number 271 from Table A. The result is then the effective spoke length of 263 millimeters. On the website, we can find another spoke length calculating system using a database of rims and hubs. Up until now, we've only looked at the theoretical aspects of building a wheel. Now comes the more interesting, hands-on part of crafting a wheel. We wheel builders do not like valve holes, which have seldom been deburred. In order to remedy this problem, we use this 90-degree deburring tool. On rims without eyelets, the nipple holes should also be deburred from the inside. If one doesn't do this, then the nipples, especially those made of aluminium, become damaged easily with high spoke tension. The tool needed is a 90-degree deburring tool, 7.3 millimeters diameter, and a cordless low-speed drill. We use the deburring tool, working hole by hole. Finishing at the valve hole. On tubular rims, the valve holes are usually drilled too small in the rim bed. As a result, the tubular does not lie flat in the valve hole, which means that with every turn of the wheel, the tire bounces uncomfortably. We solve this problem by countersinking the valve hole. The tool we use is a 90-degree deburring tool, 13.4 millimeters diameter, and the cordless drill. To insert the nipple into the rim, we need the following tools. For beginners, a number 3 screwdriver will do to start. With more advanced wheel builders, we use so-called nipple drivers, which are operated by hand. One tool works best for classic round-headed nipples. The other works like a socket wrench for hexagonal-headed nipples. The nipple driver works like a clutch, which means that as soon as the point of the tool comes into contact with the head of the spoke while it's turning, the tool no longer tightens. This means that when the spoking is finished, all the nipples will have been threaded to the same distance, making the truing process much easier. This tool for hexagonal head nipples has no clutch. So we just put the wrench on the nipple head and we turn the nipple until the thread can no longer be seen. The method one uses for spoking a wheel does not make a difference in the quality of the wheel. We're going to show our method. It's very easy to learn, and every step is very clear. One side of the wheel, the right side, is always completed first. Then the wheel is turned over and done methodically by the same process. This way we always keep track of where we are. Before we begin spoking, we check the number of holes on the rim and the hub. While working, a good wheel builder always holds the wheel the way it sits in the bicycle as if you were behind it. Which means that on the rear wheel, the freewheel or sprocket is on the right, while on a front wheel, the disc brake should be on the left. In the workshop or in a store, it also looks professional if the wheels are hung from the ceiling in this way. The spoke threads are oiled, and the alloy nipples are sprayed with oil from the outside. We start first on the right hub flange with only 2 spokes. In radial spoking, use holes 1 and 2. Both spoke heads outwards. When crossing once, use holes 1 and 4. Left spoke with the head outwards, right spoke with the head inwards. Crossing twice, holes 1 and 6. Left spoke head outwards, right spoke head inwards. The most popular number of crossings is 3 times. Here, holes 1 and 8. Left spoke head outwards, right spoke head inwards. Crossing 4 times with holes 1 and 10. Left spoke head outwards, right spoke head inwards. The number of spokes on the wheel makes no difference to the position of the starting spoke in the hub and the rim. Whether there are 18, 24, 28, 32, or even 36 spokes to put in. We will now spoke a 3-cross 32-spoke wheel. We should always work rationally. So we've prepared the nipples and spokes in advance. First we take 2 spokes. We put in 1 spoke with the head outwards, and we count the holes. 1, 2, 3, 4, 5, 6, 7, 8. And then the second spoke comes from the inside out. These are starting spoke 1 and starting spoke 2. With starting spoke 1, we go 1 nipple hole left from the valve hole. And with starting spoke 2 into the second nipple hole to the right of the valve hole in the rim. Then we put a nipple on each spoke and turn it 2 or 3 times. Now we put a spoke into every second hole after the starting spoke, with the head outwards. One, 2, 3, 4, 5, 6, and 7. With the second spoke in the left hand, we pass the rim while covering the spoke thread so that it doesn't scratch the rim. The spoke is placed in the fourth free nipple hole in the rim. Then the next spoke. 1, 2, 3, 4. 1, 2, 3, 4. And finally, the last spoke of this group, 1, 2, 3, and 4. Now we have 7 spokes left to put into place. In order to do this, we turn the wheel over. And we put the spokes in from this side. One, 2, 3, 4, 5, 6, and 7. Here is the valve hole and starting spoke 1. We turn the wheel. We take the next spoke with the left hand and count. 1, 2, 3, 4. Now the first side of the wheel should be completed. But first we still have something to do. We turn over the wheel. With a screwdriver or a nipple driver, we push each spoke crossing towards the hub. This way we straighten out the spokes. The right side of the wheel is now completely spoked. We turn over the wheel. The left side of the wheel is then spoked in the same order as the right side was before. We once again begin with the 2 starting spokes in holes 1 and 8. where do we place these spokes in the hub flange? Here is the position where starting spoke number 1 is to be put in. First, we must separate these two spokes to make a passage for starting spoke 1. Now we must first put in starting spoke 1 into the rim. We turn the wheel, take the spoke with the left hand, and place it in the nipple hole to the left of the valve hole. Now we must place the second starting spoke. We count off 1, 2, 3, 4, 5, 6, 7, and 8. This spoke is put in from the inside out, which means with the head inwards, and is put in 2 nipple holes to the right of the valve hole. So we can see the 2 starting spokes are in place. Now we put in the 7 spokes with heads outwards in every second hole, by separating, as before, the spokes beneath to make a passage. 1, 2, 3, 4, 5, 6, and 7. We have 7 spokes left to place in the rim. We turn the wheel. Once again, with the left hand, we take the second spoke and place it in the 4th hole of the rim. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 1, 2, 3, 4. And now the last of these 7 spokes. We have the 7 spokes for the remaining 3 holes. We turn the wheel over and we insert them into the hub. 1, 2, 3, 4, 5, 6, and 7. This is the starting spoke. We now take the second spoke with the left hand. We cross over the next spoke and then under the following one to put it into the free hole. Continuing like this, over and under, over and under. Over and under. We turn over the wheel and again use the tool at each spoke crossing and pull in the direction of the hub so that the spokes are straightened. Now, each nipple is screwed in until the nipple driver stops. Or, with the screwdriver, until the thread can't be seen. With this 30-second spoke, we are now finished with spoking. We can now finish building the wheel which we've spoked. We must do the following so that the wheel stands up. Adjust the lateral and radial runout. Bring up the spoke tension to the right level, which means as high as the rim will allow, and then dish the wheel. The sum of the components should then make up a durable unit that will stand up to years of use. This truing stand is simple and is sufficient. At home and in the workshop, we use a sturdier and more precise device. We can measure rim deformations with optical sensors or with dial gauges. Comparing nipple wrenches would be silly. Every wheel builder has their own favorite that they're used to and that they swear by. The spoke head punch. In principle, it's a punch with a concave point. As we will see later, we use this to set the spoke heads into the hub flange. The spoke aligner, which has been made by hand, is simply a nylon rod with a notch on the end. With this tool, we straighten the bent spokes near the hub flanges. These are adapters for hubs with through axles. They're used to fix the through axle hubs into the truing stand. Another aid is the spoke holder to prevent the twisting of aero spokes by the nipple driver. And here is a nipple driver for hexagonal head nipples. And in the background we see the dishing tool for rims. The tensiometer works like pliers. We close the pliers and lay the spoke to be measured on this white line. Then we open the pliers. By the force of this spring, the spoke bends, and we can read the deflection. This spoke bends by 0.87 millimeters. Spokes of different diameters bend differently under the same tension. A conversion table is delivered with each device, where the values read by the tensiometer can be read as spoke tensions in newtons. Professional wheel builders cannot imagine working without this device. Testing and guessing the spoke tension by hand is not precise enough. Truing requires some talent for handiwork. Beginners must start by trial and error to determine which nipples should be loosened or tightened. Learning by doing. Truing is really only a matter of experience. Patience, persistence, and self-criticism are needed in order to do it well. 28-inch road wheels are more difficult to true than mountain bike wheels with 26-inch or even BMX wheels with 24-inch and 20-inch diameters. Absolute tolerances in the circularity of the wheels are often discussed. It doesn't make sense to make assertions. What's important is that the wheel keeps its circularity. A wheel that stands does not have to be retrued later on. The absolute tolerances depend upon the quality of the rim and the final spoke tension we're able to bring up. Soft, unsatisfactory work soon reaches a tolerance of almost zero. The wheel may look good, but it has no durability. It'll be necessary to retrue the wheel several times later. But if a wheel is trued professionally with high optimal spoke tension, as much as the rim can bear, then the work is more demanding, harder, and more time-consuming. The rim becomes stiff. It fights back and hardly reacts. Small tolerances are then harder to correct. Before the spoke wrench is even used, one must put a drop of oil between the rim and the nipple, so the nipple doesn't get damaged under high spoke tension. The extra oil is wiped away. Now we tighten each nipple on the right wheel side with 2 turns so that the rim is pulled to the right. We correct the lateral runout by loosening and tightening the nipples in the area of the deformation. The amount we turn depends on the amplitude of the deformation, in extreme cases up to half a turn, and for fine adjustments only about 1/16 of a turn. With every lateral correction, only a single nipple is loosened and the nipple next to it is tightened. If only one nipple is loosened or tightened, then we will accidentally influence the radial runout. With radial runout, we work differently. If the rim is deformed inwards, we loosen the nipples. And if it's deformed outwards, we tighten the nipples. In either case, we also adjust the nipples to the right and to the left. Now we start the lateral runout. With the sensor on the right side, we tighten this spoke and this one. We continue like this until there's no more runout. Once the lateral runout has been finished, we must correct the radial runout on the rim. The rim is now deformed outwards between these 4 spokes, which means we must tighten these nipples. Here is another spot where 5 spokes must be loosened. Here the radial deformation is inwards, only between these 2 nipples, so we loosen them. Now the wheel has been pre-trued. When pre-truing a rear wheel, we pull the rim to the right from the beginning. We do this until we reach optimal spoke tension on the right side of the wheel. It's only then that we can pull or dish the rim to the left. This is the best way to bring up proper tension on the left side of the wheel. Any other way is very difficult. On a simple front wheel without a disc brake, the rim is properly dished or centered from the start. The wheel has been pre-trued, but the spokes are not yet straight to the rim. The bad alignment or position of the spokes will result in a run-out of the wheel after several kilometers and will need to re-true later. To straighten the spoke to the rim, we need to do the following. We hold a packet of 4 spokes and push them together. Once, twice, 3 times, 4 times, 5 times, 6 times, 7 times, 8 times. And now, 2 spokes, left and right, that we press together. All this in order to properly position the spokes. The concave point of this spoke head punch fits exactly onto the spoke head. With this tool and 2 light taps of the hammer, we seat the spoke heads into the hub flange, thus forming a perfect fit. This goes for the inner side of the opposing flange as well. We turn over the wheel and repeat this procedure the same way. So now, all the spoke heads sit tightly into the flange. Now we slide the spoke aligner until just before the hub flange and tap the bend in the spoke so that it's flat against the hub flange. Every spoke is treated this way with the head inwards. We turn over the wheel and continue on this side. If the spoke tension is already high, then the nipple tends to turn with the spoke as you tighten it. The spoke twists and only returns to the starting position when the tension is momentarily relieved. We relieve the tension by pressing the wheel down on the workbench. We repeat this process on the wheel 3 to 5 times, taking the time after each cracking to retrue until it no longer needs retruing and will stand up. First, we place the wheel on the workbench. With the valve hole in the 12 o'clock position, left hand on the rim in the 9 o'clock, and right hand at 3 o'clock position. The rim rests in the 6 o'clock position. We press down on the rim against the workbench with full force. We could now clearly hear some spokes settling in. We turn over the wheel and repeat the same procedure. Before putting the wheel back into the truing stand, we should check the dishing of the rim using the dishing tool.
Kontrolliere ich noch die Einmittung der Felge mittels dieser Zentrierlehre.
We set the sensor on the hub lock nut.
Stelle den Fühler ein auf die Kontermutter der Nabe. Das Gerät liegt jetzt auf 3 Punkten auf.
The device sets on 3 points.
Ich kehre das Rad um.
We turn over the wheel,
Lege die
place the
Zentrierlehre
dishing tool on it,
und stelle fest,
and see that the rim is still too far to the right.
dass die Felge immer noch zu weit nach rechts verschoben ist.
We can clearly see how relieving the wheel has changed its shape. The lateral runout has been corrected. Now we must correct the radial runout. We've finished the first stage of the fine truing. We check the spoke tension on the right side of the wheel. The device shows a spoke bend of 1.86 millimeters, which means a spoke tension of about 1,050 newtons on this type of spoke. We check several spokes. One must remember that the rim must still be dished to the left. We start by tightening the left nipples by a half turn. We now check the final dishing.
Einmittung.
The rim has now been correctly dished.
Richtig eingemittet.
We push down one more time on the wheel. As we can see, the wheel does not need to be retrued after the final stress relieving. This means that the wheel we have just built will stand up. Now we begin the highlight of wheel building, tying and soldering the spoke crossings. Anyone who has a command of this, who can conjure perfect tied crossings, all exactly alike, is a master of the art of wheel building. The mission of the wheel builder, as we've already said before, is to increase stability in the crossed spoke structure. Tied and soldered spokes no longer move against each other, and the result is a solid unity of hub, spokes and rim. In addition, if the wheel encounters any sudden radial overload due to its hits from stones, curbs or potholes, then the peak stress encountered by a single stroke is decreased thanks to the dampening effects of its co-soldered spokes. This means that tied and soldered spokes support each other. A tied and soldered wheel tends to be stiffer and reacts more directly to out-of-saddle riding, as well as accelerating more quickly. A benefit with disc brakes is a shorter and more controllable delay when braking. We also attain an advantage on the front wheel. The wheel can be steered more directly and therefore more exactly. It's also interesting to know that the actual tying and not the soldering gives the added stability between two joined spokes. Soldering is only to ensure that the wire does not come undone when riding. To tie and solder, we need the following tools and aids: tying wire, a number 2 screwdriver, liquid flux, an electric soldering iron or a gas soldering torch, soldering wire, a box wrench 14 or 15 millimeters, a blue Scotch-Brite sponge, and of course safety goggles. The tying wire is made of iron with a tin surface. This layer of tin acts as a temperature indicator later when soldering. Here is a model of a spoke crossing. Here is the spoke crossing. Here we have tying wire thicker and colored red to better illustrate. We start with the tying wire from the inside to out. Bend about 3 to 4 millimeters. And first we make one wrapping. Then the second, the third, fourth, fifth, sixth, and the seventh wrapping. While doing this, we always keep the wire tight. To finish, we lead the wire from inside out and break it off on this edge. Alex starts soldering the ties using the electric soldering iron. As we can see, he's wearing safety goggles. Each tied crossing is first treated with liquid flux. Now the area to be soldered is heated up. And soon, as we see the color change, the soldering wire is put on. We heat the tie and the soldering wire. As we have a lot of wheels to tie and solder, we're working with the gas soldering torch. This way the work goes much more quickly. Here also, we must also apply the flux on each tie before soldering. We tap with this box end wrench, 14 to 15 millimeters, when the soldering is almost finished, to knock off the excess tin. We heat up the ties until the tin starts to melt on the soldering wire. At this point, we've reached the correct soldering temperature. Heat the tie, the soldering wire, reheat, then knock off the excess. Heat, solder, reheat, knock off the excess. Heat, solder, reheat, knock off the excess. Heat, solder, reheat, and knock off the excess. We've finished soldering, and now we must clean the tied crossings. We've filled this bucket with water and some detergent. With the Scotch-Brite sponge, we clean each tied crossing. The wheel has now dried overnight. We put a drop of oil on each tied crossing. We let it work in, and then clean off the excess. Where there might be small scratches on the tied crossings, the oil soaks in through a capillary effect. Later on, it will act as rust protection by repelling water. And now the work of tying and soldering is finished. Wheels that have been spoked correctly and have optimal tension sometimes need to be thread-locked so that the nipples cannot loosen. The left side of the rear wheel or the right side of the disc-braked front wheel, where the spoke tension is weakest, need this little extra help. For this, there are several solutions. One is a liquid product that has been developed. One can apply it to the finished wheel, so it's not necessary to treat the spoke thread before spoking. We put a drop on each nipple spoke junction. Capillary action spreads the product into the thread. If the spoke threads were oiled before spoking, then the thick bond created between the spoke and the nipple can be broken if the wheel needs re-truing later. If the threads have not been oiled, then the bond cannot be broken. Prolock nipples are a proven product that have threads already treated with a strong bonding agent. When truing the wheel, a special two-component adhesive activates when a high spoke tension is reached. This bonds the nipple and the spoke. Some old wheel building pros often just use linseed oil for nipple locking. This was a few years ago, but today it's been supplanted by high-tech products such as Prolock nipples. A proven trick for nipple locking, which works best on rims with double eyelets, for clincher tires and tubulars, is caulking the rim. The corks are pressed into the eyelets and against the nipple heads so they prevent the nipple from loosening. They offer extra protection against piercing the rim tape due to very high tension, as can happen on the road or on the track. After pressing the corks into the eyelets, we file them down so that the surface becomes completely smooth. This also creates an increased gluing surface for tubular tires. There are two types of tires: clinchers and tubulars. Each has its own type of rim. Tubulars have the tube sewn into the tire casing. This type of construction allows higher tire pressures, up to 180 psi. The seam is protected with cotton tape. The tubular is glued onto the rim. The clincher, on the other hand, is held onto the rim by the bead hooks, the pressure in the tube. Clinchers and tubulars exist in different sizes and widths. They have international norms under the term ETRTO. For example, this mountain bike tire has a 55-59 dimension, which means a tire width of 50 millimeters with a necessary rim diameter of 559 millimeters. The correct tire pressure is a key to safety, comfort, and smooth riding, which is why tire pressure should be checked before every ride. Most tires have the maximum pressure on the flank. Of course, tire pressure also depends on the rider's weight and the type of terrain and the tire width. A rule of thumb for road competitions is 100 to 130 psi, for cross-country 30 to 50 psi, and 140 to 180 psi for the track. Tires should be kept in dry, dark rooms. tubes are made either of latex or butyl. The most popular valves are the types Schrader and Presta. The latter is most suitable for higher pressures. We must also take into account the shape of the rim. Now we will watch how to put a new tire onto a new wheel. For this, we need self-adhesive rim tape, scissors, an awl, talcum powder, and of course, the tube and the tire. First, we clamp the wheel into the stand. We start with the rim tape exactly opposite the valve hole. We lay the rim tape all the way round, and then about 10 centimeters past the starting point, we cut the tape. Now we punch a hole for the valve using the awl. Next, we hook the tire onto the rim and push and pull it with both hands towards the floor. We sprinkle the inside of the tire with talcum powder and spread it around so the tube will not stick to the tire later. We pump the tube with just a little air. We put the valve in, then push the tube into the cavity between the rim and the tire. This should be done in a regular fashion. And now, most important, we push the valve back up before we put the tire onto the rim. The tire is again pushed against the floor and onto the rim with both hands. We check to make sure the tube is not stuck between the tire and the rim. Be careful. Tire levers are not recommended for mounting tires because the tube could become damaged. Now the tire is pumped up to about 100 to 110 psi. Here we can see how the label of the tire is centered exactly to the valve. Proof of the work of a real professional. Now we'll see how a tubular is glued correctly. For this, we need some abrasive cloth, an awl, solvent, tubular cement, a brush, and of course a tubular. First, we prepare the rim. The rim bed is sanded down with the abrasive cloth. And criss-cross scratches are made with the awl so the tubular cement will stick better. The rim is then degreased with solvent, a task that must be performed diligently. Once this is done, the tubular cement is applied to the rim regularly with the aid of the brush. The wheel is hung up for 24 hours so that the tubular cement can dry. Then we follow with a second coating of cement, which also need 24 hours to dry. The tubular is ready to be glued after 48 hours at the earliest. After this time, we begin by pumping up the tube to about 30 psi. And we apply a coat to the tube. Then the rim receives a third and final coat. We clean off the excess glue from both rim edges. The tubular is put on, the valve adjusted. Then the tubular is pushed and pulled with force towards the floor. And we finish by pulling it over the rim. We pump up the tubular to 100 psi. We then adjust the tubular, which is best done with the thumbs of both hands. Now we push the tubular against the rim with back and forth movements under the entire weight of the body until there's a full bond between the tubular and the rim. Any remaining tubular cement that's visible is removed with solvent. The wheel must be left to bond for another 24 hours before it can be ridden. Now, methodically, we'll show you how to glue track tubulars. The method is the same for both carbon and aluminium rims. We need the following tools and aids: abrasive cloth, a scraper, solvent, contact glue, a brush, And finally, the track tubular. On carbon rims, the valve hole is slightly countersunk with a scraper, so that the tire lies flat at this spot. The rim bed is sanded intensively with the abrasive cloth. The rim bed must be cleaned and degreased with solvent. Carbon surfaces have a greasy character, therefore the cleaning must be done carefully. With the brush, we apply the first 2 coats destined to the base of the rim. We let the first coat dry for at least 24 hours. When the first coat is completely dry, we apply the second coat, which we also leave to dry for 24 hours. Only after 48 hours, or better yet even longer, can the tubular be coated. Add a bit of air to the tubular and coat the band. 1 coat is enough. After 5 or 10 minutes, the last coat is applied to the rim bed and the rim edges are cleaned with solvent. We must work quickly as the tubular has to be put on the rim immediately. We pump up the tubular a little before we place it on the rim, adjust the valve and push and pull the tubular with full force towards the floor. Finally, we pull it over the rim. The tubular is pumped up to 1,140 psi and adjusted with the thumbs of both hands. The contact areas of the rim and the tubular must adhere fully. In order to properly seat the tubular, we use back and forth rocking movements, pushing with full body weight. If some contact glue is on the rim sidewalls, it should be carefully removed with solvent. The wheel can be ridden after 24 hours. As the term tubeless suggests, this is a tire without a tube. The assembly of this type of tire only works on special tubeless rims. Every rim is delivered with its own valve. The original valve is put in. The thread is greased a bit, and then it's screwed on. We wipe the tyre sidewalls with a sponge and soap to make putting the tyre on the rim easier. The rotational direction of the tyre is usually marked with an arrow, and so the tyre must be inserted into the rim accordingly. We begin inserting the tyre into the recess in the rim bed opposite the valve. The second tyre flank is put into the rim recess in the same way. One must never use tyre levers, as the tyre flanks could become damaged by them. The tyre is pumped up to the maximum pressure. If the tyre has been properly positioned, then there will be an audible sound when it's pumped up. The final check. We must check the concentricity of the tyre with the rim. And secondly, we let out the air in order to check to make sure that the tyre's sidewall adheres to the rim when there's no air pressure. We finish the mounting by pumping the tyre up once again. We need the following tools for disassembling and reassembling a cassette: a crescent wrench, a cassette remover along with a chain whip, a quick release, grease, and of course a cassette. Firstly, we grease the outside of the cassette body. And then the inner thread of the lock ring. The sprocket package is inserted, paying attention to the splines, as there's only one way it will slide on. First, we screw the lock ring on by hand. Then we put the wheel on the floor and use the crescent wrench and the cassette remover to tighten firmly. The quick release axle is greased before skewing it into the hub. The cassette's taken apart by using these two tools. Before assembly, we grease the sprocket threads. The sprocket is screwed on by hand. Then it's tightened as much as possible with the chain whip. We then oil the axle threads before putting on the axle nuts. Today, lock nuts are no longer used even by track sprinters. Track clinchers are pumped up to 140 to 180 psi. 2 layers of rim tape are used so the tyre does not pull off from the rim, and so that the increased pressure does not cause the tube to wear a hole through the rim tape. With the awl, we punch a hole through the rim tape for the valve. The quick release lever is always on the left side of the bike, as viewed by the rider. The clamping force of the quick release is set by tightening the nut until significant pressure is needed to flip the leader closed in a horizontal position. To take off the rear wheel, we must shift to the smallest gear. Then open the brake calipers and the quick release. With the left hand, we hold the left seat stay while rising the bicycle from the floor. We push the rear derailleur back with the right hand and we let the wheel fall. The wheel is reassembled in the reverse sequence. Don't forget to close the brake calipers. On this wheel, a spoke is broken at the elbow. This is a typical fatigue brake. The spoke is taken out and a new one put in. The spoke thread is oiled. The nipple put on and screwed on. Now the wheel must be trued. If a rim needs to be replaced, then we can reuse the spoke structure with intact spokes. This only works if the rim is of the same make and type or has the same rim diameter. We will need the following tools: an axle holder, a nipple wrench, a nipple driver, self-adhesive tape, scissors, and oil. The wheel is clamped with the axle holder into the vise. We place the new rim on the old rim, being careful to line up the valve holes. Now we tape both rims at 3 evenly distributed points. Starting at the valve hole, we first loosen the nipples on this side of the rim with 2 to 3 turns so the spokes are detensioned. Then we turn over the wheel and loosen the nipples on the other side of the wheel. Beginning again at the valve hole, we unscrew the first nipple. We oil the spoke thread lightly. Place the spoke in the new rim and screw a new nipple in. Never, never reuse old nipples. Once all the spokes have been placed in the new rim, we take off the self-adhesive tape. We remove the old rim and true the almost new wheel on the truing stand. Often a hub is defective and must be changed on the wheel, or all the spokes must be replaced and washers put in because of constantly broken spokes. The rim, however, is in perfect condition and can continue to be used. We need the following tools and aids: a nipple wrench, a spoke cutter, and very importantly, safety goggles and protective gloves. When removing spokes from the rim, we must be careful not to warp the rim permanently by gently loosening all the nipples. This 2 to 3 turns at a time until the spokes can be removed by hand. Be very careful. If the spokes are under the slightest tension, they can shoot like bullets through the workshop. They can become very dangerous projectiles. We take off all the spokes near the hub with a spoke cutter. Caution, as soon as the work with the spoke cutter begins, it's important to wear protective gloves. Those who do not wear glasses must absolutely protect their eyes with safety goggles. We must be careful of the ends of the cut-off spokes, as they're as sharp as needles. Rim brake surfaces must be cleaned from time to time in order to maintain braking efficiency. Specialized stores may sell abrasive rubber blocks. With these, the entire brake surface is smoothed under light pressure until it shines.